Hi, 8th graders. So we're going to start chapter 10. We're going to jump right into chapter 10, section 2, where we are simplifying radicals. Section 1 was Pythagorean theorem. We already went over that. That was an entire lesson on geometry, so we're not going to rehash that. So jumping right on in, simplifying radicals. So we have some key terms here. First is the radical expression. This is an expression that contains a radical. If you don't know what a radical is our square root symbol. We call it a radical because we also have cube roots and fourth roots. And so depending on what exponent we are doing the inverse of, our radical could contain that number symbolized for its root. But that symbol itself is a radical. A radical expression is simplified if the following is true. So we have three things in order to know that we have a simplified radical. Our radicand, that's the number inside, or actually not just the number, but everything inside my radical, that's called the radicand, has no perfect square factors other than 1. So, I can't divide the number by 4, 9, 16, all those perfect squares. They're not present on the radicand, which is the number inside. The radicand contains no fractions, so we shouldn't have any fractions inside our radical, and no radicals can appear in the denominator of our fraction. Then we're also later on in videos, we're going to talk about how to rationalize the denominator. This is the process of removing radicals from the denominator because they won't always our denominator radicals will not always be perfect squares. And so there will be times where we have to take care of and do we call it rationalizing the denominator. So that's what we have in store today. This first video, we're going to focus on just simplifying the radicals and not so much worried about the rationalizing the denominator yet. That's for a video down the road. So first video here, we're going to talk about the multiplication property of square roots. And so this multiplication property of square roots just states that if inside my radical a times b would be the same as saying the square root of a times the square root of b. So what that's basically saying is I can look at this number 48 and say, you know what? I know that the perfect square that goes into that is 16. And that 16, we'll put this all under, 16 times 3 gives me 48. Therefore, I can do the square root of 16 times the square root of 3, which will give me the square root of 16 is 4 radical 3, or square root 3. And then that's my simplified radical. Now, some of these you are going to be able to spot the perfect square off the top of your head. I'm going to admit that sometimes I struggle to find the perfect square. And so I'm going to give you this tried and true way. And actually it was the pre-calc teacher in Leavenworth, when I taught there, taught this method to me and reminded me about factor trees. So you may remember doing prime factor trees in elementary school. Hold on, there we go. You may not. So I'm going to show you, but the prime factor trees work whether you know your perfect squares or not. So if we're being honest, it took me some work to find the fact that it was the largest perfect square was 16 that went into 48. But when I look at this, I know, maybe you look at it and you're like, well, I know 4 goes into 48 12 times, right? Or this is another version. Maybe you didn't know 4 went into 48 and you knew that 2 went into 48 24 times, right? And then we just keep bringing it down until we're just prime factors. So like 4 becomes 2 and 2, 12 becomes 2 and 6, 6 becomes 2 and 3. Or if I'm over here, 24 is, maybe you come up with 6 and 4, 6 is 2 and 3, and 4 is 2 and 2, right? Notice we come up with the same factors, right? The fact that we have 1, 2, 3, 4 twos, 1, 2, 3, 4 twos, and 1, 3. I'm not worried about the numbers that we're treeing off. I'm only worried about the numbers I end with. And so the way that these prime factor trees work is because I'm doing a square root, I'm going to pick out my pairs. I want them in groups of 2. And so, and it's the same over here. Once I have my groups of 2, anything that pairs off goes to the outside, right? So I had a 2 and a 2, and left inside Netflix and chilling is my 3 all by itself. And then we just simplify. 2 times 2 is 4, and we end up with the same thing for square root 3. So either method works. If you can easily pick out your perfect squares, go for it. And just think of it as the square root of this perfect square times what is ever remains, or what that perfect square times gives you your number you're inside. If you're like, I struggle to notice those or know my perfect squares, then these prime factor trees are for you. And again, it doesn't matter how you tree off. Notice again that I have this pair of 2s and this pair of 2s, and this 3 is by itself. It is the same thing, so it doesn't matter how I factored each of these numbers. I'm going to end up with the same thing in the end. So those are just a couple methods. So here we have 160. So like I said, I like to use my prime factor trees. Now this one, easy enough, 16 and 10, right? And so 16 is 4 and 4, 10 is 2 and 5. I will admit, if you notice it at this point, that there are no other perfect squares in this, right? 16 was that perfect square. Then you can really stop right here at this pair of 4s. Because this isn't going to pair off to anything. These are going to pair off to 2 2s, right? Which you can go to. But I know that there's that 4, and so I'm going to have 4 on the outside. Now, I have 2 and 5 left inside my radican, and so then this becomes 4 square root 10. And that's our answer. That's how we go about simplifying square roots. Now, what happens when we add a variable into it? Not much. Not much happens at all. So we're going to start with the 54, and I know that 54, 2 goes into that, and 27 times, and 27 is 3 times 9, and 9 is 3 and 3, right? And so I can pair it off. I've got one pair of 3s, and then I'm left with a 3 and a 2, right? So I know right now, just number-wise, I've got a 3 on the outside with a 2 times 3, which is 6 on the inside. That's what I'm working with the numbers. Now, when it comes to my exponents here, my variables with the exponents, we're going to do that. Just don't forget that our root, it's like a fraction, right? So this would become into the 7 halves, and then I just simplify that out. How many times does 2 go into 7? It goes in 3 times. And so because it goes in 3 times, I'm going to come out with an n cubed outside of my square root and left with an n inside. And then I just combine these. Everything outside goes together. So this becomes a 3n cubed, and inside becomes a 6n. And as you get further and further into this, you don't have to do them as 2 separate problems like I just showed you here. You are really just going to do them as one problem and work it out all together. I just wanted to show you how we work the numbers and how the variables work. And so that's why I did it separately, as if they were different. But they're not. So again, when it comes to the variables, really you're just dividing your exponent by 2, and anything remaining, which really should only be a 1 since we're doing square roots, will remain inside the radical. we have just a couple more to fit in. On these, when we are multiplying, remember when we multiply, we can multiply them together. It goes both ways. Not only can I split it out, but I can also multiply them together, outside with outside, inside with inside. But when I do that, I like to simplify as I go. So like, I know that there's a number that if I took 7 times 14, we're going to get. So I'm just going to act as if we treat off and have 7 and 14 as our 2, right? And then I know that 14 is 7 times 2. And so I know that on the outside, we're now going to have 7. But I already have a 2 and a 3. So right now on my outside, I have 2 times 3 times 7. Also, this t won't simplify, but this t squared does, bringing a t out to the front. And I'm going to have the square root. We're left with a 2 on the inside. And this t right here, that t is left inside as well. And then from there, we just simplify. 2 times 3 is 6. 6 times 7 is 42. And so we end up with 42 t square root 2t. And that's our final answer. Now, you could have taken the 7 times the 14, got whatever. The number would have been up here. What that would be like 78 or something like that. 98. But we end up with the same thing in the end. So like I said, I like to take whatever's inside my radicals. Those numbers become the first pairing off for my tree. That's the way I do it. If you have questions on that, I'm happy to help you with it. All right, so now what happens when we have to actually apply it? So we have a rectangular door I'm going to draw, because that's a way to problem solve, right, is to draw our situation. It's not square, but there's our door. A rectangular door in a museum that is 3 times as tall. I forgot to go in and fix that. 3 times as tall as it is wide. So here's our width, and we know that it's 3 times our width is its height. What is a simplified expression for the maximum length of a painting that fits through the door? Well, the maximum length would be that we take that painting through the diagonal, right? And so then what that creates is a right triangle. And so we want to find this distance, that length right there. So our diagonal squared is going to equal our width squared plus our length squared. And then from here, we're just going to simplify. So we have d squared equals w squared plus, and then 3 squared is 9. So we have 9w squared. We're going to simplify or combine like terms. So we're going to end up with 10w squared. And then I want to know the diagonal. I don't want to know the diagonal squared. So we've got to square root this. And so d is going to equal, there is no perfect square in 10. So, but the w squared is a perfect square. So w square root 10. And that is our simplified expression. And so that's where we end up using, could end up using simplified expressions. So then once I measure the width, then I know the actual maximum length of a picture that would fit through that doorway. But that would work for any and all doorways that have those dimensions. So that is simplifying expressions. We're looking for those perfect squares. If it helps to write down all your perfect squares, again, I highly recommend those prime factor trees. They always seem to work faster for me because I don't have to think about perfect squares. In the next video, we're going to talk about what about fractions and rationalizing denominators. So I'll see you there.